So for the last part of our discussion video, we have here two more examples. For the first one, you're asked to set up a definite integral equal to the area of the portion of the cylindrical surface y equals 2 minus x cubed, bounded below by the xy plane, above by the plane y plus z equals 2, and whose portion on the xy plane has endpoints 0, 2, and 1, 1. We start by sketching our cylindrical surface. So for this case, um, if we suppose that this is the z-axis, this is the y-axis, and the x-axis respectively, then notice that for our cylindrical surface y equals 2 minus x cubed, we're missing the z variable, so we're sketching here a plane curve on the xy plane, and we extend that along the direction of the z-axis. So to sketch first the plane curve y equals 2 minus x cubed, again we have here the portion on the xy plane with endpoints 0, 2, and 1, 1. So to plot, say these are y equals 1 and 2. This is the point with coordinate 0, 2, while for the point 1, 1, if I say that this is 1 for x, the point 1, 1 is given now by this point. And so, um, since we only need the portion of the surface y equals 2 minus x cubed in between the point 0, 2, and 1, 1 for its portion on the xy plane, basically need here this portion of the curve. The question now would be, up to where do we extend this portion on the xy plane? So normally, that is from math 22, we extend this towards the direction of the missing variable. But since our surface here is bounded above by the plane y plus z equals 2, then at whatever point lying in between here, the points 0, 2, and 1, 1, the z value would depend here. So that is, for example, if I take for this case the point 0, 2, x is 0, y equals 2. When x is 0 and y equals 2, the corresponding z value here is 0. So we still get this point. While for this point 1, 1, x is 1. When y is 1, z would be equal now to 1. And so, again, when x is 1, y is 1, we extend this up to the point when z is also equal now to 1. And so to sketch here, or to plot the point, you have here this portion, and so the extension is up to this portion only. Again, notice here that for this point 1, 1, we get to extend that up to this portion. For this point 0, 2, there's no need to extend since this is already a point on the plane y plus z equal now to 2. As for the points in between the point 1, 1 and 0, 2, again from 1, 1 going to 0, 2, the y coordinates in fact increase. But as the y coordinates increase, the corresponding z value here would also decrease. And so what we have here would look something like this for a cylindrical surface. And so you have now the following. So in fact, it is not needed for you to sketch this cylindrical surface. We basically need to identify two things: the function we need to integrate, and then over what curve C do we integrate that function. So again, recall here that what we want would be the integral over C of f of xy ds for the surface area, where here the curve C is actually the projection of the cylinder onto the xy plane. But for this example, the projection is given by this curve, and we obtain this coming from y equals 2 minus x cubed. So C in fact is given by y equals 2 minus x cubed. So for its parametrization r of t, x is the independent variable, so we could set that as the parameter. Y is automatically given by 2 minus t cubed. Where t for this case, again, t, the parameter is given by x. So x here, notice, runs from 0 up to 1. So t is from 0 until 1. computing for r prime, since we need this for ds later on, r prime has components 1 and negative 3t squared, in which case its norm is equal now to the square root of 1 plus 3t squared quantity squared, that would be 9 times t to the fourth power. While for the function f, again recall here that this is given by the height. The function f for this case, just the height function, notice that the height here is when the cylindrical surface in fact intersects the plane y plus z equals 2. So the height is given by whatever z coordinate do we obtain here. But the z coordinate obtained for this part came from y plus z equals 2. So that would be 2 minus y. So this is our function f of xy. And so the surface area is equal now to the integral over c of 2 minus y ds. And again, this is equal now to the integral from t here is from 0 to 1. 2 minus y will now be 2 minus t cubed. And then ds is replaced now by the square root of 1 plus 9t to the fourth multiplied by dt. And so this is equal to the integral from 0 to 1 of 2 minus 2 minus t cubed would be t cubed times the square root of 1 plus 9t to the fourth power dt. And so this is our final answer since we're simply asked to set up. However, notice that you could actually integrate this expression. And so if you could practice as an exercise, um, please verify that this definite integral is actually equal to 10 square root of 10 minus 1 all over 54. So this ends our first example. If you have a question, you may feel free comment down below, or you may rewind this video or this part. We now proceed with our last example. So for this case, let's find now the mass of a thin wire formed into the shape of the helix with x equals t, y equals cosine t, and z equals sine t. T runs from 0 until 2 pi, given that the density at any point is equal to the square of its distance from the origin. So for this item, since we want to compute for the mass, recall here that m is equal to the integral over c of f of xy z ds, since we're situated in the three-dimensional case, where here c is the shape of the thin wire, while f is actually the density function, in which case the shape of the wire is given by the helix, so c given by r of t is equal now to the vector with x component t, y component cosine t, and z component sine t. And t here is from 0 until pi, for which case r prime of t is now the vector with components 1, negative sine t, and cosine t. And so the norm of r prime of t is equal to the square root of 1 plus negative sine t quantity squared is sine squared t plus cosine t quantity squared is cosine squared t. And so this is equal now to the square root of 1 plus sine squared plus cosine squared is 1. So we have here the square root of 2. While our density function f of xyz, as stated in the problem, is equal to the square of the distance of any point from the origin. So that would be the square of the distance of xyz from 0, 0, 0. So that would be square root of x squared plus y squared plus z squared quantity squared. Or that is basically x squared plus y squared plus z squared. And so the mass now is equal to the integral over c of x squared plus y squared plus z squared ds, or that is, this is equal now to the integral from 0 going now to 2 pi x squared is t squared plus y squared is cosine squared t plus z squared is sine squared t. And then ds is replaced by the norm of r prime, which is square root of 2 dt. Or this is equal now to the square root of 2 times the integral from 0 to 2 pi of t squared plus cosine squared plus y squared. Uh, Cosine squared plus sine squared is 1 multiplied by dt. And so to integrate, we have here the square root of 2 times antiderivative of t squared is t cubed over 3 plus antiderivative of 1 is t, evaluated from 0 until pi. And so this is equal now to the square root of 2 multiplied by, when t is equal to 2 pi quantity cubed is 8 pi cubed over 3 plus 2 pi. When t is equal to 0, this is equal now to 0. And so we have here the following answer, which actually ends our examples for today. So if you have any question, feel free to comment down below, or you may ask your discussion teachers regarding what to do or for clarifications. If you want to answer some problems, you may take a look here at the following exercises. You're not required to answer the following, but we'll be uploading an answer key um, for these exercises in the Ovlet page. So this ends our discussion video for this lecture.